Welcome to another edition of RCE. Again, I'm your host, Brock Palen. You can find us online at rce-cast.com. On there, you can find a link to a list of all the existing shows that we've already finished. You can download the full MP3, subscribe by iTunes, RSS feed, and all that stuff. You can also nominate topics for future shows. We're always looking for topics coming in from out there in the community and what people would like to see. Today I have a guest from, I believe, Sandia National Lab. He can correct me. He's a developer for the piece of software otherwise known as IceT, which I believe is a parallel image compositing engine. I know nothing about these things, so I'll let him introduce that and he can correct me. Ken, why don't you go ahead and introduce yourself?
All right. Well, like you said, my name is Ken Moreland from Sandia National Laboratories. You got that correct. My experience is in parallel, distributed, and scalable graphics and visualization. I got my start in this field about 10 years ago, where we were working on IceT itself, and I've gone on to work on very large distributed systems. I am a regular developer, for example, of the ParaView large-scale visualization system.
Okay, so why don't you go ahead and tell us what IceT is?
All right. Well, as you basically alluded to, IceT is a library to assist in large-scale distributed memory parallel rendering. The name IceT is an acronym for Image Composition Engine for Tiles, and at its core is a set of very fast image composition algorithms. Now, the basic idea is to take a collection of images, each with partial information, and combine them to one complete image. And this is a standard technique for parallel rendering for close to 2 decades now. What makes IceT truly unique is that we can perform this image composition on large format tile displays, and I know of no other system that is capable of doing that.
Okay, so this is one thing where I ran into trouble searching for this because there happens to be a certain wrapper out there known as IceT. What is the official spelling of IceT? And I know there's an entire paragraph on the IceT website about this.
Yeah, so it's a long and rather stupid story. So originally IceT wasn't called IceT, it was called MTIC for multi-tile image compositor or something silly like that. And one of my colleagues came up to me and said, you've got to rename it because no one can remember that name. And at the time, for some reason, I thought it had to be an acronym that actually made sense. So I thought very long and hard about something that was pronounceable, and I came up with IceT. For Image Composition Engine for Tiles. And originally it was all caps with a dash, and for some reason I saw people using camel case, probably because you can't use a dash in identifiers in C code. So I switched to using the camel case, but you still see both in practice. Neither of them Googles very well, so if you want to look for it, you should type my name in and then type IceT and it'll show up.
Okay. So how did you exactly, where did the idea for IceT come around? Was it just the age of the existing algorithms out there didn't map to newer systems?
No. So what happened was that this group began experimenting with parallel rendering in the late 1990s. And at the time, most of the large-scale visualization was done on what we called big iron SGI machines. There's these big, expensive boxes with lots of memory, lots of cores, and most importantly, lots of graphic pipes put together in a computer that was about the size of a refrigerator. But because they're expensive, there's this growing movement to use the much cheaper consumer-level graphics cards. And the best part about it was the performance of this consumer-level graphics cards was growing at an astonishing rate. So there was a plethora of research into the software solutions for driving these distributed graphics. Now, we were being funded by DOE ASCII, and ASCII was and still is about large-scale computation to support science. So our goal was rendering capacious amounts of geometry that was generated by these large-scale computations. So we did a lot of research that analyzed the behavior of the different parallel rendering approaches that were available. There are different techniques, sort first, sort last, but we quickly concluded that the sort last algorithms were the way to go. The way the sort last algorithms work is that the rendering primitives are statically assigned to processes, and all the processes render a full-size image with partial geometry. Then these images can be combined together to form a single correct image. So the great thing about this is that it has wonderful scalability, which is what we're most concerned with, this large amount of geometry that you want to render. And simply adding geometry amortizes the cost of the sort last parallel rendering algorithm. However, the biggest drawback both back then and today, was that bigger image means more overhead. So at the time when we set out to perform sort last on 60 million pixels, it was really a crazy idea. But the idea that we had behind IceT that nobody else seemed to, well, very few people actually seemed to address, was that geometry is seldom uniformly distributed spatially. Geometry tends to implement spatial coherency, which simply means that if the geometry is close together in memory, it's probably also close together spatially. And when you have spatial coherence, that means when one process renders its geometry, it's going to render its data on a very small part of the screen. And that's going to leave a lot of the pixels blank and they can be ignored. When you're on a tile display, that means a lot of the tiles can just be thrown away. So the algorithms in IceT are designed to throw away these blank tiles and balance the compositing of the remaining sparse set of tiles.
So I've seen the sort first, sort last stuff appear in what's the piece of software? Chromium, which I believe is now a defunct project, but that was actually for GL acceleration rendering. Is IceT involved in the hardware acceleration pipeline, or is this before you even get to those calls?
It's actually after. So IceT stands back and lets you render the geometry in any method that is most applicable to your application. Most typically today that means using something like OpenGL to render something on a GPU. After that rendering is finished, remember the rendering is done on a partial set of geometry. You grab these images back, and then IceT works generally at the CPU level and message passing interface to combine these images into a single cohesive unit that you can show to the user.
How does IceT know like where things are placed in memory then if the geometry is already done? I guess I'm not quite following what's going on here.
Okay. The way a sort last algorithm works is that it doesn't really matter where the geometry is. So each process renders its geometry locally to an image. And not only for rendering an opaque surface, you'll render both the colors that you'll see on the screen, but you'll also render a Z buffer, which is for each pixel how far away the nearest polygon was. Then you read back the color and this depth, and then you can what you call composite the images together. So on a pixel by pixel basis, you look at the Z buffer and you see which pixel is closest, and you color it by that color. And of course, IceT's algorithms do this in a parallel nature, so they'll be doing this over so many processes, passing messages back and forth.
So you mentioned you work on ParaView, and actually ParaView and a similar piece of software called Visit is where I first learned about IceT. You can use those in a tile environment without IceT. Are they just using stuff that like comes with VTK, or what exactly is? So you described what IceT does. What are they doing in these other methods that is so much slower than what IceT is doing?
All right. I can't speak to Visit, but I can speak to ParaView. When you use ParaView now, it's always using IceT for its tile display rendering. There is a mode where IceT will just go behind the covers and let you distribute the geometry across everything to make things go faster. But in general, the only parallel rendering implemented in ParaView is IceT, and that's because it's the fastest algorithm we have available.
Okay. So what I was reading must have just been referring to IceT becoming standard, and they just stopped calling it IceT.
Yes. Most likely because IceT has taken over all the parallel rendering in ParaView. Okay. Oftentimes people don't even bother to say it anymore. Okay,
so the next thing I had was what was the relationship between IceT, ParaView, and Visit. I didn't know that you worked on ParaView before now. So, of course, ParaView is the primary consumer of IceT, or is there other products out there that use IceT?
So ParaView was certainly the first, and that's simply because we went from developing rendering algorithms like IceT to working on full systems like ParaView. So when we started developing within ParaView, we became insistent on using efficient rendering libraries, and of course we liked IceT because not only was it ours, but it's again the fastest one we had available. Since then, I know of a few other projects that started to work with it.